Let's say we take a 6-volt lantern battery and connect a wire from the negative terminal to one plate of a parallel plate capacitor and the other wire from the positive terminal to the other plate. Then the top plate is lacking in electrons and becomes positively charged. Those electrons are moved or conducted to the negative plate, and then I can ask this question: what if we replaced the 6-volt battery with a car battery, which is 12 volts? What happens to the capacitance? So maybe we take a look at this equation for capacitance and think, as the voltage increases, what happens to the capacitance? And you might be led to say the capacitance goes down because voltage is in the denominator, so it appears that there's an inverse relationship between capacitance and voltage. But that's not what happens at all. If we were to replace the 6-volt with the 12-volt, the capacitance would stay the same. What happens is it gets twice as much charge. So as voltage goes up, capacitance stays the same, but the charge goes up by the same amount. So that the ratio of charge to capacitance stays constant, and that, after all, is how we define capacitance. Keep in mind, the capacitance is really affected by its dimensions, the distance between the plates and the area of the plates. So this equation for capacitance doesn't show us how we can effectively change the capacitance. This is just a very basic equation that helps define what capacitance is all about. If we want to affect a change in the capacitance, then we need to use the equation that tells us how area and plate separation. So if I want the capacitance to go up, I can decrease the spacing, or I could increase the area. Either one of those would make the capacitance increase. This is similar to the equations that describe the way in which a convex lens works. So convex lenses are used in movie projectors. A piece of film is illuminated and becomes the object, and light is passed through the lens, and then the image appears on the screen. Now you know there's a relationship between object and image according to the lens equation. It says the inverse of the focal length of a lens is equal to the inverse of the object distance plus the inverse of the image distance. But there's also an equation that says how we can make a lens. So the lens maker's equation is a little different. Let's draw in the intersection and show that a convex lens is made of two curved surfaces, each with some radius of curvature. So the front surface has a radius of curvature of R1, and the back surface of the lens has a radius of curvature of R2. The focal length of that lens is equal to the ratio of the index of refraction of the lens material divided by the index of refraction of whatever surrounds it. So maybe the lens is made of glass and the material that surrounds it is air. So take the ratio of these indices of refraction minus 1 and multiply that by the inverse of the radius of curvature of the front surface minus the inverse of the radius of curvature of the back surface. Okay, so what does this equation tell us? As the object distance is increased, so let's say there's a knob on our projector that moves the film, and it makes the distance between the film and the lens, which in this diagram would be here, larger. What does that do to the focal length? It seems as if focal length is dependent on object distance, but it's not. No matter what, the focal length will stay the same. It's not as if moving the film in any way can change the radius of curvature of the lens. It certainly isn't going to make the lens change from glass into plastic, right? This isn't sorcery. The focal length is going to stay the same as long as there's no change in the radius of curvature of the material that makes up the lens. So, as object distance increases, the image distance is going to decrease, but the focal length stays the same. So, if that analogy helps you distinguish between what the equation that defines capacitance tells us versus the equation that tells us how we can design a capacitor, then feel free to keep that analogy in mind.